Today, we're going to continue looking at sequences, series, and power series. We've talked about the way we think about these things. A sequence is just a list. So term 1, term 2, comma, term 3, and so on. And the question is, does the sequence converge or diverge? And sequences are the simplest ones. A sequence converges if the terms have a limit. A sequence converges if the terms have a limit. Sequence converges if the terms have a limit. So if the limit as n goes to infinity of Sn exists, then we can say that the sequence converges. So all we have to look at is the limit as n goes to infinity of Sn and whether or not that exists. A series converges if the sum is finite. A series converges if the sum is finite. This is a much more complicated question. But we're looking at the sum. What we need to be able to determine quickly if the sum of an is finite. This is a bit of a tricky question. We have to be able to look at the form of the terms an and decide quickly whether that is a convergent series or a divergent series. In the case of a function, the question is, where does the power series converge? For what values of x is the series convergent? So the question here is, for what values of x is the series Cn x to the n convergent? So when we plug a value of x into a power series, we end up with a series. So we plug stuff into this function, and instead of getting real numbers like we had before, like we have with our regular functions, we end up with a series. And so the question is, do we get a convergent series or a divergent series? So the question is not, does the power series converge or diverge? The question is, where does the power series converge? So all seems to focus on series and being able to determine when a series converges. So our goal, we need to be able to determine if a given series converges or diverges. So our job is now to be able to determine if a given series converges or diverges. That's our goal. All right. Okay, so let's talk about determining whether a given series converges or diverges. I don't know if this is the pens or if it's the paper or the not paper. So the game we want to play is that I give you a series and you determine if it converges or diverges. We have to be able to identify all the conditions under which a series will converge. And we have to be able to do this quickly just by looking at it. The same way that when we look at a function, we have to determine if it what's in the domain and what's not in the domain. If I give you the function 1 over x minus 5, we can see right away that 5 is not in the domain. There are certain things that have to happen that we have to identify immediately so that we can quickly determine. We tend to present this as a series of tests, a bunch of tests that we apply to the series. And so it kind of creates this idea that to determine if a series converges, we apply some test to it. But that's not really how it works at all, because some of the tests, to determine if they converge or diverge, to run the test, you actually have to know if the series converges or diverges before you run the test. You can't do the test without knowing. There's one test that works where it's like, oh, I don't know if it converges or diverges, let's run a test. But that's generally not how this works. You just have to know. And so the question is, how do we know? We look at lots of series. And then you guess, converges? And I say, no, that diverges. And then you're like, oh, why? Because the p is equal to 1/2. And so that's the game that we're going to be playing. Ultimately, this comes down to a multiple choice question. It's absolute convergence, conditional convergence, or divergence. It's one of those three things. At the beginning, I only care about two, convergence or divergence, and then we start splitting convergence up. So what this means, since it's multiple choice, all you have to do is answer. This is one of those times where it's appropriate to take off points if you don't answer. So I do the opposite of what the SAT does and like the standardized tests. The standardized tests penalize you for getting a wrong answer, but there's no penalty for not guessing. And I think that's exactly backwards of what should be done. What should be done is that the penalty should be applied for not guessing, especially on something like a multiple choice test. The answer is right there in front of you. Pick one of them. And then all we need to do is realign the way we do education in society so that we don't stigmatize people that get things wrong, because getting things wrong is the whole point. There's no point in having school if everybody's just going to get everything right all the time. You know what I mean? So anyway, in my world, there'll be a penalty for not guessing. You can't win if you don't play. Let's talk about convergence of series. The game is going to go like this. Given a series, we got to get used to the way we're going to abbreviate these things. Given a series, sum as n goes from 0 to infinity of an, which will be a0 plus a1 plus a2 plus a3, and so on forever. We want to determine if it converges or diverges. Then later on, we'll split convergence up. We will usually abbreviate series an by leaving off the indexing. So n equals 0 to infinity. Where we start the counting is not relevant. What's important is that the terms are going to infinity. This is the important part of the series. This is where convergence happens or divergence happens, not here at the beginning. So if this sum, a0 all the way out plus a1 plus a2 all the way out to infinity, if that's an infinite sum, subtracting a1 through a3 is not going to make a difference. You subtract some finite amount from an infinite amount, it's not going to make a difference. We are usually going to abbreviate series. just by saying sum an. That is, we leave off the indexing. We leave off the indexing because that's understood. It's understood that we're going to be going to infinity. And since we're going to infinity, it doesn't matter where the n starts. So it's understood that we're going to infinity. It's understood that there are infinite terms, because if there aren't infinite terms, convergence is not a question. It's understood that there are infinite terms because if there are not infinite terms, then convergence is not a question. Convergence only comes up in the case of infinite series. If there's a finite number of terms, then we're going to have a finite sum, and we don't have to worry about it. It's only when there's an infinite number of terms that we care. So that's why we get to abbreviate just series an. Number two, since there are infinite number of terms, it doesn't matter where the indexing starts. The convergence and divergence doesn't happen in the first part of the series. It happens in the ... It happens at the infinite end of things. So since there are infinite number of terms, where we start is not really important. Where we start the terms isn't important for the question of convergence or divergence. If it's a series that we can actually find the sum, then where we start matters because we're actually adding things up. But if it's just a question of does it converge or diverge, is it just a question of is the sum infinite or finite, then it doesn't matter where we start the terms. If the series as n goes from 0 to infinity diverges, the series as n goes from a billion to infinity also diverges. We can cut off 10 to the 10th terms and the series will still diverge. We can cut off a huge amount and the series still diverges. This is how big infinity is. All right. All right, and 10 to the 10th is actually a pretty large number, but if you're really concerned that that's not a big enough number, there. Still diverges because I've still only cut off a finite amount. Even though we're dealing with unfathomably huge numbers. I think I saw somewhere that if like the Milky Way was the size of North America, then Earth is like not even a speck of dust on the counter. And we've only sent a signal out to like the driveway. So it's kind of ridiculous. It's unfathomably huge. And then since things are going to infinity, it's just more. All right. So we have this is all just the abbreviation. Well, we're going to be lazy. We're going to abbreviate the sum AN. Let's talk about what we can look for to determine if a series converges or diverges. First thing to look for, if the limit of the terms is not 0, then the series diverges. First, most important thing to look for, if the limit of the terms of the series is not 0, then the series diverges. Notice that we're making a distinction between the terms of a series and the series itself. When I put the sigma in front of it, this series AN, this is the series with the sigma. But when I'm looking at the limit as n goes to infinity of AN, I'm just looking at the terms of the series. Where I don't write the sigma. If the limit of the terms is not 0, then the series diverges. If the limit of the terms is not 0, then the series diverges. So here's how we write it with our abbreviations. But what we're saying is if the terms of the series, if the limit of the terms if the terms of the series don't go to 0, then the series diverges. That's how we would say it in just regular old words without our abbreviations. So for example, if I have a series as n goes from 0 to infinity of n squared plus 1, so this will be the series 1 plus 1 squared is 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. We can see that this is going to make an infinite sum. We can see that the sum is going to be infinite. We can see that the series diverges. To justify that, we would say that the limit of the terms is not 0. Therefore, the series diverges. The limit as n goes to infinity of n squared plus 1 is not 0. So the series n squared plus 1 diverges. Note that the limit as n goes to infinity of n squared plus 1 does not exist. We would not want to say that it equals infinity because equals infinity doesn't make any sense in and of itself. It gets the idea across. That's how in math we might write, when we're being lazy, this limit goes to infinity, or these terms go to infinity, but we don't say equals infinity. That's bad language. So the limit of the terms is not 0, so the series diverges. Another example of some terms that we saw the other day, but in sequence form. So here's the series where the terms look like 3 plus 2n over 7 plus 5n. This series is going to diverge because the terms don't go to 0. So we'll start off with 3/7 when n equals 0. And then the numerators we're adding to, so 5, 7. And the denominator we're adding 5, so 7, 12, 17, 22, 27, and so on. This series diverges because the limit of the terms is not 0. The limit of the terms is not 0, so the series diverges. Notice it's not the limit that diverges, it's not the terms that diverge, it's the series that diverges. We got to make sure that we get our words matched up correctly. Limits exist or don't exist. Series converge or diverge. We wouldn't want to say that the series doesn't exist because there it is. If we think about what's going on when we say that the limit of the terms is 2/5 and not 0, what this sum eventually looks like is a bunch of things that are very close to 2/5. So in the long run, this looks like plus 2/5 plus 2/5 plus 2/5 plus 2/5, and so on. For large values of n, this is what the series looks like. And we keep adding to the sum some positive amount that's not close to 0. And so the sum is just going to keep going. If we think of in terms of the sequence of partial sums, at this point we add another 2/5. Then the next term in the sequence of partial sums increases by 2/5. Then the next term increases by another 2/5. The sequence of partial sums could not converge in this scenario because we're not adding something that's close to 0. So if we think in terms of the sequence of partial sums, this can't converge. This is all because if the terms of the series don't go to 0, then the series diverges. If the limit as n goes to infinity of an is not 0, then the series an diverges. A very important distinction we need to make. If all we had to have is that the limit of the terms is 0, so the series converges, then this whole section would be a lot shorter. Unfortunately, logically, the only conclusion we could make from the original statement is that if the series converges, then the limit of the terms is 0, but we don't get the converse of that. or the inverse. I can't remember. We get if A, then B, then if not B, then not A, but we don't get B if B, then A. So we have a statement that has this form: if A, then B. And so that gives us if not B, then not A. But we do not get B implies A. So when I make the statement, if the limit as n goes to infinity of an is not 0, then the series diverges. What we get from that is the contrapositive. If the series converges, then the limit of the terms is 0. That makes the limit of the terms being 0 a necessary condition, but it is not sufficient. So we do get the contrapositive. I think it's the contrapositive. Now I can't remember. So we do get the contrapositive. I'm going to call it the contrapositive until someone corrects me. So maybe there'll be an angry comment on the video, on the YouTubes. Probably not. Not many people are watching and commenting on the videos. Not that I really want you to. I'm just saying. No one's going to notice if I call this the contrapositive. So the contrapositive says that if the series converges, then the limit of the terms is equal to 0. If not B, then not A. So the limit of the terms equals 0 is a necessary but not sufficient condition for a series to converge. So this statement here is necessary but not sufficient for convergence. And this is an important thing to think about. We need to look at what we're saying. We're saying if the limit as n goes to infinity of an is not equal to 0, then the series diverges. That is saying a necessary condition for convergence is that the limit of the terms is equal to 0. Unfortunately for our heroes, this is not a sufficient condition. Any questions? This is just playing the logic game, a class that is very useful to everybody that we make sure that we don't offer. So good job, educational system. Probably the best preparation for, we used to. I had a formal logic class when I was a student at CSM, and it was a great class, and probably one of the more important classes that I ever took moving forward moving forward into my upper division math work. I don't know why, but I think it's just not because I was like writing down formal logic proofs like this all the time, but that kind of thinking made me a very careful reader for things. It's also why, even though I don't believe that a dungeon master needs to remember all the rules, as a dungeon master, I do remember all the rules. So anyway, I think it comes from that class. And we can see the lack of formal logic training in, well, every comment on the internet ever. I'm not saying that logic works. Logic absolutely does not work. As soon as someone starts bringing up logic in an argument, you know they're floundering. You know they're going to be suffering, because that's not how to convince people of things. You know what I mean? Facts and logic, they just don't work. That's not how it works. And anybody that starts appealing to facts and logic is really going after your emotions, which is what does work. You know what I mean? All right. That's all beside the point. The important thing is that the limit of the terms equals 0 is a necessary but not sufficient condition for convergence. So just for a quick example, in the waning minutes of class, the series 1 over n squared converges, and the series 1 over n diverges. In both cases, the limit of the terms is equal to 0. That's a necessary condition, but there's some sufficient condition that makes 1 over n squared converge, but 1 over n does not. So the series 1 plus 1 over 2, 1 over 4 plus 1/9 plus a 16th, that converges, but the series 1 plus a half plus a third plus a fourth plus that series does not converge. There's a version of a math joke. I saw someone get a math joke wrong, which is always the worst. Never go for the math joke unless you know it's correct. And the math joke goes, an infinite number of mathematicians walk into a bar. The first mathematician orders a beer. The second mathematician orders a half a beer. The third mathematician orders a quarter of a beer. The fourth mathematician orders an eighth of a beer, and so on. And the bartender sees where this is going and says, okay, I get it. And he just pours 2 beers. And then someone messed up the joke because they're like, oh, an infinite number of mathematicians walk into a bar. And I'm like, oh, I see where this is going. The first one orders a beer. The second one orders a half a beer. The third one orders a third of a beer. And I'm like, oh, you've already messed it up. I see what you're doing. And you're giving me a divergent series, not a convergent one. The bartender is going to need an infinite number of beers. So this sum is equal to 2. Someone should check me on that. And this sum goes to infinity. Questions? So what I really want to drive home today, the walk away from today, is that if the terms, the limit of the terms equals 0 is a necessary but not sufficient condition for convergence, and that is why it's the first thing that we check. So this series here fails the first thing that we check. The limit of the terms is not 0, the series diverges, we're done, we move on. When the limit of the terms is 0, then we have to look closer. That's all we wanted for today. Our necessary but not sufficient condition, so that tomorrow we can start building up a list of sufficient conditions. Any questions? Comments? Deep thoughts? One final thing for the DVD bonus material, the series 1 over n diverges. This is the border. This is where things change over. 1 over n squared is on the convergent side of 1 over n. Think about what would look like on the other side of 1 over n. What else would be the divergent side? Think about that. That'll do it for today. Everybody have a good day. I'll see you tomorrow, and thanks for playing.